Welcome to this Analysis Junior Seminar. Today with us we have Ivan Prusak. He discussed his PhD thesis just in December. So today he's a postdoc here at SISSA MATLAB, and today we'll talk about an optimization-based, fully segregated reduced model for free structure interaction problems. So please, Ivan, you can start.
Thank you, Anna. Welcome everyone to my seminar. As Anna said, an optimization-based, fully segregated reduced order model for free structure interaction problems. Let me move a bit stuff. Okay. So this is part of my PhD project, which was carried out here at SISSA under this supervision of Dr. Monica Nonino from the University of Vienna, Dr. Davide Torlo, and Professor Gianluigi Pozza at SISSA. Okay, sorry. Okay, so the main two packages we used in our numerical simulation are the Phoenix project and the Urbanics package, which is based on Phoenix and which was developed in the MATLAB group here at SISSA. The outline of my talk would be the following. First, I will introduce an optimization-based domain decomposition formulation of the FSI problem. Then I will introduce an effective iterative Gauss-Newton optimization algorithm in order to decouple the solutions of fluid and structural subproblems. And then we move to POD Galerkin order modeling, and then I will show some numerical results. So we will start with first the formulation of the FSI problem, and for that we consider the following domain, where we have in blue the fluid domain, and in black the structure domain, and here in kind of red we have a free structure interaction interface, which is moving in time. In the fluid domain, we consider the Navier-Stokes equations and the incompressible Navier-Stokes equation, while on the structure subdomain, we consider the inner system model. And the structure equation is governed by the second P-Euler Kirchhoff tensor, which is given as follows, and the structure and the fluid part is governed by a Cauchy stress tensor, which is given here. And then the problem is also completed with some boundary and initial condition, which is the following. And in order to complete the whole problem, we need to impose also the conditions on the interface between the fluid and the structure subdomains. And in the case of free structure interaction problems, we consider three different types of interface conditions, which are the following. The first one is the continuity of the velocities. It is a kinematic condition which imposes that the fluid is attached to the interface to the free structure interaction to the free structure interface. Then we have the balance of stresses. This is the classical action reaction principle, which states that the normal fluxes on the interface are equal. And then we have a continuity of the displacement, which is a geometrical conditions, and state that the fluid domain and the structure domain do not overlap over time. As it is very important to notice that by convention, the fluid part and the structure part are defined on different types of domains. In fact, for the Navier-Stokes equation, we consider the Ablerian formulations, and for formulation, and the equation are described on the moving fluid domain, which depends on time. Whereas for the structure equation, we define the equation on the reference configuration. And in order to be able to describe the interface condition in the mathematical way, we need to introduce some kind of mapping between the reference and the parent domains. And the classical one of the classical approaches there are which we use here is a so-called arbitrary Lagrangian invariant formulation. For that, the idea behind is to introduce a time-dependent map which maps the fluid reference configuration at any time instance into the domain which we have at time t. And this map is defined as follows, where we need to define where we introduce a new variable which is called a fluid displacement. And in our case, we decide to describe the fluid displacement as a harmonic extension of the structure extension on the interface. Actually, this is not the only way to describe. That's why the formulation is called arbitrary. But for the purposes that we have in this work, it is enough to consider the harmonic extension. Okay, then. Now, having at hand ALE map, we can write the interface condition in the mathematical form. And for that, we first need to provide a deformation gradient, which is the following, which is just the gradient of the ALE map, and we also need its determinant. And with this, we can write the interface condition in the following form, where here we have the continuity of the velocities on the interface. Here we have the balance of stresses, and here we have the continuity of the displacement. And then we have the representation of the Cauchy tensor in the reference configuration. Okay, sorry. So having posed a fully coupled problem, we move to the variational in space formulation. For that, we need to introduce the variational spaces, which is the following. We need a space for the fluid velocity, the fluid pressure, two spaces for real and test spaces for fluid displacement, because as I mentioned here, we have a Dirichlet condition on the interface, and then we also need a space for the structure displacement. And okay, we have a fully coupled system. I will not get much into details how we get it. If we have time, we can discuss it after the presentation. But as I mentioned, the problem is fully coupled because the fluid part depends both on the normal stress function, which is defined on the interface, which enters the fluid momentum equation and also the structure equation. And then all of them are coupled through extension equation, where we have that which depends on the structure equation itself here on the interface, and it enters into in the definition of the on the fluid equation, which is now defined on the reference configuration. Then we move to the time discretization. We divide the time interval in some way for as it's given here, and then we provide a discretization for the fluid velocity for the first derivative of the fluid velocity and the second derivative of the structure displacement. And with that, we can describe the fluid structure interaction problem, the time discretization of the fluid structure interaction problem using the completely implicit scheme. I want you to notice that we already here can decouple the extraction equation from the rest of the problem by using some kind of extrapolation of the fluid displacement by using the previous time step instances for example as it's given here. Now, then we move to domain decomposition. And our approach, as it's mentioned in the title, is the optimization-based. So for that, we use our interface condition. First, I mentioned at the previous slide that we already decouple the fluid displacement from the rest of the episode problem. So basically, this condition is already used in some way. So now, and then we can use the following as the continuity of the velocities and the balance of stresses in order to pose an optimal control problem, which hits as follow. We want to minimize the difference between the fluid velocity and the second order approximation of the derivative of fluid displacement, while using the normal stresses on the interface as our control variable, which enters the fluid moment. Yes.
Sorry, I always lose it here. Like,
okay.
So can you tell me what is the optimal control statement? I am very layman about that.
Okay.
Yeah.
So we have a coupled fluid structure interaction problem, and we have some conditions on the common interface. So the first one is the continuity of the displacement have been dealt in the previous step. And then we want to decouple the problem by putting the other two conditions. So in our setting, okay, it can be used, okay. There are actually two choices in this step, but either one is to minimize the difference between the velocities of the fluid part and of the fluid velocity and the structure displacement, which enters here, and then we have the other one as a control variable, which enters the fluid momentum equation and the structure equation, which is basically our normal stress on the interface.
What is G? What is G?
Is a control variable that enters here, but it's connected to the normal stress on the interface. Okay, here we have that like the normal stress function enters both the fluid momentum equation and the structure equation, and it is the same function here. So the point is to find such a G such that putting instead of GI, we have the fluid velocity as close as possible to the velocity of the structure. I hope.
So that is the objective that you are trying to minimize.
Yes. So the objective I'm trying to, so we need to minimize this functional over G. So we need to find G such that this difference is as small as possible, and that G enters here, which is our Forest function. I hope.
Yeah.
Okay. Then, as I mentioned before, the fluid displacement is pre-computed, and it is very important as first step, because now I want to move to the analysis of the optimal control problem, which I just stated. A key element of the optimal control problem analysis is to provide the a priori estimates for the fluid velocity and pressure, and also the structure displacement. I will not go into details here, but it's okay. It's like using the classical properties, you can obtain the following type of the a priori estimates here, which basically depends on the per-computed fluid displacement and all the variables that are which are known at the time step Tn, and also it depends on other control. Here P is the second order polynomial, which depends on these variables, and here same. If we depend, the structure displacement is bounded by the known values from the previous time step and our control variable here G. And as it goes in optimal control analysis, first we need to describe an admissibility set. So this set is composed of all the points in other variational spaces, such that they satisfy state equations, which are our fluid and structure subproblems, and plus that the objective functional is finite. The admissibility set is non-empty. There are actually a few reasons for that. Okay, maybe the easiest one is that, like, when we take G equal to 0, then we lose the coupling between fluid and structure equations, and in that case, the fluid and structure problems are well posed. So we can solve the solution belong to the admissibility set. Then, since the admissibility set is not empty, we can choose a minimizing subsequence inside the set, and such that the values over this sequence converges to goes to the infimum over all points in the admissibility set. Then okay. So since because of this, and because of how we define the functional J gamma, we see that G is bounded, that the sequence G is bounded in L2 sense. And then putting this into our a priori estimate, we can also deduct that is sequence that correspond to fluid velocity, fluid pressure, and the structure displacement are also bounded in the corresponding spaces where they are defined. And for that, we can deduct that there exists a subsequence of the original sequence with the following convergence properties. As the fluid velocity and pressure and the structure displacement subsequences converges in the weak sense in the corresponding spaces here. And since the VF and ES are the subspace and as subset of the H1 spaces, we can also deduct that they due to the compactness inclusion that they converge strongly in the L2 sense, and plus we have again by the compact inclusion of the trace spaces, we can also deduct the Stokes the strong convergence of the traces of the subsequences in the L2 sense on the interface. Okay, and then we can by using all these properties, we can pass in the limit in the equations, and we can deduct the point at we that okay. First of all, okay, this sequence, because of this convergence, converges to some point like this, and because we can pass provide a limit in the equation in the free structure interaction equation, we can deduct this point is inside our admissibility set. And then, because the objective function is Laver semi-continuous, we can if we have the following property, and since the minimizing sequence is actually the infimum, so we can conclude that this point is actually the minimum of our functional. Okay. This is if we come back just for a second to the form we use the functional, we had this extra term here which was essential in order to provide an optimal control analysis, because we had we could conclude the H2 boundedness of the sequence G. There is also a way to prove the existence of a minimizer when gamma goes to 0, which is a very essential step, because we want to because in fact we want these two conditions to be satisfied. So we want our fluid velocity to be as close as possible to the structure to the structure velocity. Okay, I will not describe how we did this, but actually it's very similar to the way we did the existence analysis in case of where gamma is greater than 0, and if you want, we can discuss it later after the presentation. Okay, and now comes the problems of uniqueness. Actually, it's a very hard task, and we couldn't prove it analytically because first of all, the fluid problem and the structure problems are very and structure problem are very complex in themselves, and we have the uniqueness of the solutions only when we impose very smooth data. And in general case, we cannot deduce the uniqueness of the optimal control problem, but in the numerical test, we always got the convergence to the monolithic solution, which is a state of the art, which is the state of the art up to now. Okay, then okay. I will stop here with the optimal control analysis, and then now we can move to the how we can actually work with what we have at hand. In order to deal with the optimal control problem, we resort to so-called non-linear least square setting, and which is basically we write our objective functional in the following form, where the functional is defined on the L2 spaces here, and the operative functional can be seen as L2 norm minimization of this functional here. And for that, there exists a very effective optimization algorithm, which is called Gauss-Newton, which is iterative optimization algorithm. And I will quickly describe what we need for that. So for that, we need to define and control rational approximation, which is taken from the previous time step. And then during the iterative procedure, we can solve this state fluid and the state structure equation in the parallel. Then we can update the fluid displacement by using the value of the structure displacement on the interface. And then we can update the surge direction in the iteration process via conjugate gradient algorithm. Here we can actually see the code. Okay, so we have the inertial approximation, which is taken from the previous time step. We impose the maximum number of iteration and the tolerance, and the optimization process stops when either the maximum number of iteration is reached, or when this this value is less than the set tolerance. And inside, we first solve fluid and structure equation in parallel, as I said, and then we update the structure the fluid displacement by using the structure displacement, which we just solved before that. And then we update using the conjugate gradient algorithm with the partial derivative of the functional n and its adjoint. Also, we have obtained the analytical formulation of the partial derivative and its conjugate. Then, okay, this is all done as a continuous level. Now we can move to the discretization. In our work, we concentrated on using the finite element method, and for that, first of all, we need to describe finite dimensional subspaces of our variational spaces. And since the fluid part, which are incompatible with Navier Stokes equation, have a subdomain structure. We need to guarantee that the fluid velocity, pressure, and the displacement spaces are insubstable in the following way. And then we can discretize a non-linear least square functional, and now we can use a Gauss-Newton optimization algorithm. And in this case, the optimization problem is finite dimensional. The dimension of the problem is equal to the number of degrees of freedom on the interface, which is the dimension of the finite element space XH. Okay. And also, we assume that the finite element approximation is good enough so that we can now move to the part of the reduced order modeling. In the reduced order modeling, we assume that we have at hand the parameterized FSA problem. The parameter can come either from the internal state of the model itself, from the boundary conditions, and also in other cases, since we work with the non-stationary problem, time becomes one of other parameters as well. Then we provide a sampling of the parameter space, because the parameter space is usually a hypercube, so it is uncountable and infinite. So we need as a finite sampling. Then we solve a high fidelity, which is our finite element optimization problem for each parameter in the finite set. And then we store the sets of snapshot for each of the variables separately. As I mentioned, the fluid part has a saddle point structure. So we also need to build in substable spaces also at the reduced order level, and for that we use a so-called supremizer technique, which consists that for each snapshot of the pressure of the fluid pressure, we solve the following equation in order to find a supremizer variable as pH, and then we store an additional set of supremizer variables. And then having at hand the snapshot set, we can rely on the POD compression, which consists in following. We define the correlation matrices for each of the snapshot sets. Here's the inner product for the variable star is defined and is the same as it is defined for the finite element subspaces. And then for each of the correlation matrices, we define an eigenvector problem of the following form, where Q is the eigenvector matrices, and lambda star is a diagonal matrix which contains all the eigenvalues in the decreasing order. And then we define the POD basis in the following form. Also, this form guarantees that the POD bases are orthonormal. Then we form a reduced basis for each component separately by putting the first so-called most energetic POD modes, and then the fluid velocity reduced spaces are enriched by the span of the pressure supremizer modes. This is done, as I mentioned, in order to obtain the pair of the fluid velocity and pressure spaces to be in substable. As we could have noticed, I did the POD compression only for the fluid velocity, pressure control, and the structure displacement. And here we use a different technique for the fluid displacement. And the technique is the following: instead of using the POD compression, or instead of storing all the fluid displacement structure and performing a POD compression, which is quite costly, having advanced the structured displacement POD mode, we can solve a harmonic extension, and then a harmonic extension when we use the value of the interface from the structured displacement POD modes. And for that also here it enters that we don't need the Lagrange multiplier or some other techniques, because the fluid displacement problem has a non-homogeneous bounding condition. And in the online phase, we rely on the collecting projection of the RV spaces, and then the fluid displacement, because of the structure we defined here, is obtained by using the reduced expansion coefficient by the of the structure displacement. And then we again can use the Gauss-Newton optimization algorithm. Here it actually is the same algorithm that we used at the continuous level. The only difference, the main difference here, as I mentioned, that instead of solving the harmonic extension in order to obtain the fluid displacement, we just use the reduced coefficient for the structured displacement, and we obtain the fluid displacement as a span of the fluid of this fluid displacement basis functions. This is basically okay. Now we can move to the numerical results, and here I will introduce a 2D thermodynamic problems and other if we consider the following geometry in the reference configuration. In blue we have the fluid domain, in red the structure domain, and in green in our fluid structure interface. I'm sorry. And then we impose the following boundary, and in initial conditions we impose that no slip conditions on the fluid walls here and here. Then we impose a free outflow and the part of the boundary gamma out, and some impulse on the part of the boundary gamma in for the fluid part, where the pressure in profile is given by the following function here. And also we assume that the structure is attached to the walls of the fluid here. And at the initial time step, we assume that the fluid and the structure are at rest. Then here we have the computational details of the offline phase. Okay, I would like you to note. Okay, first of all, we use 3 different parameters in this first case, actually 4 with time. Our physical parameters are the maximal pressure at the inlet boundary and two Lamé coefficients that enters the definition of the second P-Oleg Virchow tensor. And then I would like you also to notice that the structure density and the structure and the fluid densities are almost the same, and I will explain why this is important later in the talk. Okay, providing a POD compression, we can see the decay of this values, and we can see an obvious exponential decay. The smallest decays is shown by the fluid velocities, so that it gives us the idea that for in order to approximate the fluid velocity, we need a high number of reduced basis function. And here I present the decay of the full order model and the order model for the Gaussian parameter value here as a final time step, and also I indicate how many POD bases we used for each of the variables in our problem. We can see that the obviously the convergence of the convergence of the functional the full order model is slightly better than as a ROM case, but also if you can from the errors, we can see that even with a quite small number of the POD modes, we can see a very good approximation of the problem of the components as a reduced order model. Here we can see how the solution changes in time. Okay, and here we can see the difference between the full order and reduced order model and its monolithic counterpart. We can see that the reduced order model has some difficulties at the interface and close to the boundary, but still the differences are quite acceptable. And then we provide the computational time per each time step, and on average we have 8 minutes in case of the full order model, and from 1 to 3 minutes at the POD Galerkin case. It's very important to mention, since we have another problem, that this time can be significantly decreased if we apply some hyper production technique, which wasn't done here, and we expect that first time can be a matter of seconds, but it will be done in the future. So here in first talk, I introduced the optimization-based domain decomposition with other model framework for FSA problems. Then I provided some details in the analysis of the optimal control problem that we had, and provided an efficient optimization solver, which led to full decoupling of the fluid and the structure subproblems. As a other model, we applied POD Galerkin technique, which led to the reduction of the problem dimensions, and also we had reduction in terms of the number of optimization iterations. And as I mentioned before, I wanted you to notice that here that the fluid and structure densities are close to each other, and this is actually here. Enters here that our method is stable in case of so-called added mass effect, which is the main added mass effect occurs when the fluid and structure velocities are very close, or when the domain has a very slender structure, and it is the main cause of instability of the completely partitioned approaches in fluid structure interaction problems. And as it is evidenced by our numerical results, both form and raw models are stable under the added mass effect. And in the future, if you want to concentrate on the multi-domain decomposition, then we can also introduce domain decomposition inside fluid and structured domains. Then we already working on non-intrusive artificial neural network based or just other models. It will be also very interesting to consider the combination of different digitization techniques on different subdomains for examples when you can use finite volumes for the fluid part and FEM for the structured part, then it's very important to incorporate hyper reduction method in order to decrease the computation time at the on the online stage. And then there is always an interest to consider a more complex multi-physics problems. That's it on my side, and here you can see some bibliography, and if you have any questions, I will be very happy to answer. Thank you for your attention.
Thank you, Ivan, for the nice talk and presentation. So, are there any questions from the people here in presence? No? Okay, maybe I have one quick small question. I saw that for the full order model, you use the first order time discretization, right?
Yes.
Implicit.
Yes.
And for the reduced order model,
Same.
also first order. And
Yeah,
have you tried with a second order or more accurate time discretization?
Not yet, actually. Yeah, but I mean, if we like as a just other model, we use the same order of discretization in time, because we basically just provided the collecting product of the equations. So basically, it wouldn't make much sense to use as a just other model, because we won't gain much more accuracy, which is of course driven by full order model. It would be interesting to use it first in the full order model and then see how it goes into which is order model. But otherwise, it doesn't make sense.
Okay, thank you.
Yes.
Are there any questions from the online part? Okay.
There is, okay.
No.
Mm.
I don't see questions from online, so please.
Yes, I contact when I said actually, just in terms about the last part on the models, I wonder.
Yes.
How you compare solutions that are on different snapshots and that's different geometries.
I mean, because of the ALE map, we basically like all our snapshots are defined on the yes.
Everything is done on
Yes.
and then that is to go back to your results.
Yes.
On the errors.
Yes.
So first of all, I'd like to understand the snapshot. How many snapshots you compute?
It's
what do they represent? I guess they are positions of the structure.
Yes. You can also I mean, how many? Okay. So basically, we compute. So we define. Okay, so we have a three-dimensional parameter space in the physical domain, and we draw specific for parameters, and once we have a 10 and we have 100 time steps. So in total, we have 6,400 snapshots in general, and we're three of the 100 POD modes in the POD compression. And then we choose a number of the POD modes in order to generate just basis spaces by using the decay of the string values. Our Lamarck coefficient, time, Lamarck coefficient, and also the pressure which enters here. So we consider like both in the fluid domain, on the structure domain, and time. Basically, we try to mix everything in order to see how it works. Yeah, and
when we're comparing the errors.
Yes, here you mean?
So, since so what you have on the top is the error for the full.
Or the model with respect to the monolithic solution.
With the same part.
Yes, at the final time step. Yeah.
So the error seems better,
Which is expected. Yeah.
So I wonder then if instead of doing it to show the model, I can compute, a coarse solution of the full model.
Okay.
That's my question.
It could be. It's interesting actually. I mean, well, okay. For the solution on the full order model, actually, like, it is actually the mesh we chose, which was quite fine, but I mean, if you use the outer mesh, the full order model is not as good in order to catch the interest in order to catch the proper sorry, I will come back here. No, sorry. Because here at some point at the edges of the interface, we have in time some kind of vortices around, okay, not vortices, but very strange floor, because we have a non-convex domain at some point in the fluid part.
There are features
that is not fair. Yes, exactly. Yes, exactly, because they come from the POD modes. they are already present in some way in the priori modes.
Yeah, the comments on this. Also, the theoretical computing between the full order model and the monolithic solution, they're on the same meshes. So we're not comparing the full order model with an analytical solution or something that can mesh. So it might be that error is not just more validation of the full order model, which is consistent with the displacement, with the monolithic solution. So it's really with the analytical. So the error might be larger than what you see there.
Okay. So are there any other questions, curiosities? Okay, I guess no. So thank you everybody for being here today. Thank you again, Ivan, for your presentation, and see you at the next AJS.
Thanks. Bye.